Hello folks, this is Dr. Young, and in this video we're going to talk about Dalton's law of partial pressures. So this will be used for when we have mixtures of gases instead of just some pure gas. So before, we talked about the ideal gas law in the previous three videos. We found missing variables using PV equals nRT. We were able to combine that equation when we had a single gas that had a variable change, like you just changed the temperature or pressure, something like that. That was the second type of ideal gas law problems. And then we saw that we could use it in chemical equations where a gas is one of the reactants or products. Now, in this video, we're going to extend that into gas mixtures. Right, so before we were just talking about pure gases, right? So we just had one type, only one type of gas. But remember that the identity of the gas never really mattered. Like we didn't care if we were talking about helium or neon or hydrogen gas or oxygen gas or nitrogen gas. We didn't really care. The same thing is going to be true when we have these mixtures of gases, right? So I have a mixture here. In this case, I have two. So two or more gases. And what we're going to see is that the identity of the gas is still pretty irrelevant. I don't really care if it's a red one or a blue one. It's just that I have more gas particles. But I can say things about the individual gases if I know the relative amounts of those individual gases. So Dalton's law of partial pressure basically just says that the total pressure of a mixture of gases is the sum of all of the partial pressures of the gases, right? So where this is the total pressure, right? The total pressure, hence the T. That's why it's got the subscript of T. And then these are all of the partial pressures of however many gases there are. I just stopped at 4, but if there were 3,000 gases in your mixture, you'd have 3,000 partial pressures. If there's only 2, you'd have only 2. So these are all the partial pressures. All right, so these would be all the partial pressures of, gas 1, of gas 2, of gas 3, etc. Right? All of the however many gases you have, you just add them all up. That's all that Dalton's law of partial pressures is. You're just going to add them all up. Now, what's interesting though is that this will extend to this other interesting observation, which is just that whatever the fraction is of one gas in your mixture is, that's going to be the fraction of partial pressure that it exerts in your mixture. So if you have a gas that's half this and half that, the total pressure will just be divided in 2 for those two gases, right? That each of those gases will contribute half of the partial pressures to that total pressure. What that's saying here is that if you look at this partial pressure of some gas, gas 1, that partial pressure is going to equal the mole fraction. That's what this chi is. Mole fraction of that gas, which is chi. That's supposed to be a chi, Greek letter chi. And you just multiply that by the total pressure. Just multiply that by the total pressure. So if your total pressure is 3 atmospheres and one of your gases makes up 1/3 of the mixture, then that means that gas is exerting 1 atmosphere, right? 1/3 of the total pressure. That's all it's saying. Whatever the proportion of moles there are of the gas, that's the proportion of the pressure that it exerts. So what is this mole fraction of gas? I'll talk about this more in a second, but this mole fraction here is just the moles of a gas, so I'll just say moles of gas A, divided by the total moles of gas. Right, so if you want to know the mole fraction of some gas, it's just the part over the whole. It's like any other fraction, right? Part over the whole. So the moles of A over the total moles of gas, and we'll apply this in some future ones. But what I want to show you right now, just so you can kind of visualize these mixtures a little bit and see the proportions work, I have a FET simulation that I want to show you. All right, so here's a FET simulation that we can use to kind of observe Dalton's law of partial pressure. Remember that Dalton's law of partial pressure just says that the total pressure of a mixture of gases is going to be the sum of the contributions of each part. So let's do this, right? Let's say I add 200 of this blue type, they're calling it heavy versus light, but the blue type of gas. I'm going to start this, so there's 200 of those. I'm going to raise the temperature of this a little bit, just kind of get them moving. All right, so I'm going to let those gases kind of fill the area. So what we're saying is, what I'm learning from this right now is that when I add 200 particles of gas, moles of gas, if I add 200, that the pressure is 30 atmospheres. All right, so 200 brings me to 30 atmospheres. So that means that every 100 particle, another way to say that is that every 100 particles is worth 15 atmospheres, right? Apparently every 100 particles is worth 15 atmospheres. So I know, and that's going to be of any gas particle, right? Remember that ideal gases, they pretty much all behave the same. When they're ideal, they all behave the same. So it doesn't matter what the identity is, right? If I raise this to 300 particles, I should go up to 45 atmospheres. But if instead of raising the blue one to 300, what if I get to 300 but I use the light ones instead? So if I use the light ones, the red ones instead, that should still raise me up to 45 atmospheres if I go to 100. Right? I know that if I get to 300 anyway, whether it's from 200 or whether from 300 blue ones or from 200 blue ones and 100 red ones, I should get up to 45 atmospheres. So let's see what happens when I add 100 light ones here. Add 100 light ones. Sure enough, boom, I went up to 45 atmospheres. And I'm willing to bet that if I add another 100 light ones, I'm going to get up to 60 atmospheres. And sure enough, I get up to 60 atmospheres, right? Because again, the sum of the individual pressures from these individual gases is going to equal the total pressure of this, right? Similarly, I could take away all of the blue ones. If I take away all of the blue ones, I'm going to have half as much gas, so I should have half as much pressure. So I should go down to 30. Let's see if that works. Took away all of the blue ones, boom, I went down to 30. Right? So when you mix these gases, you're going to change the total pressure. That's all Dalton's law of partial pressures is saying. And it's saying that the partial pressures for each gas is proportional to its mole fraction, to its percentage of each thing, right? So when I have these equal, when it's 50-50, like I have now, 200 and 200, and I'm up at 60, that means that each of them contribute 30 atmospheres of pressure, because it's 1-to-1, so you can just divide this by 2. However, when it's not 50-50, if it's something like 33% and 66%, now I know that of this roughly 45-ish, about 15 atmospheres is coming from the heavies, and about 30 atmospheres is coming from the lights. Because the proportion of the actual gas particles is the same proportion of the pressures being exerted by those particles. That's what this is saying. So let's look at some math. Exactly what does this look like? So hopefully you saw, right, in that simulation, just that when we add more gases to a mixture, we increase the pressure, right? The pressure is just the sum of all of the partial pressures of those gases. So here are some questions, here are some mathematical questions relating those topics, so the first one, right, so if I want to look at just the total pressure as a mixture of gases, it's the sum of all the partial pressures. In this example, if in the atmosphere, the partial pressure of nitrogen is 0.78 atmospheres, and the partial pressure of oxygen is 0.21 atmospheres, and the partial pressure of argon is 0.01 atmospheres, what is the total pressure? Well, I'm just going to take this equation here, right, saying that the total pressure is going to be the partial pressure of N2 added to the partial pressure of O2 added to the partial pressure of argon. So I literally just need to go up here and see like, oh, nitrogen is 0.78 atmospheres. O2 is 0.21 atmospheres. And argon is 0.01 atmospheres. And if I add all those up, I get that the total pressure is 1 atmosphere. Which is, right, not a shocker. 1 atmosphere, that is the pressure that we're in. But this is the mixture of gases that we have, right? It's mostly nitrogen and oxygen, and there's a little bit of other gases, argon being one of the main constituents of the remaining gases. So you literally just add up all the partial pressures to get the total pressure. That's it. Now, what if we have a question where we have to use this mole fraction idea, right? So here's a question. In a sealed container at 15.7 atmospheres, a sealed container at 15.7 atmospheres contains 2.1 moles of nitrogen, 6.8 moles of helium, and 1.9 moles of hydrogen. What is the partial pressure of each gas? Right, so I need to kind of do two things here. I'm definitely going to use this equation where I have my partial pressure equation. So let's just start with the nitrogen. Let's say I want to see what's the partial pressure of nitrogen. I know that that's going to be that's going to equal the mole fraction of nitrogen times that total pressure. But first, if I need to figure out what is that mole fraction for N2. And right, so I just need to, again, part over whole. So I just put how many moles of N2 there are, which is apparently 2.1 of N2, over how many moles total. So I'm just literally going to add up all the moles. So there's 2.1 from nitrogen, plus 6.8 from helium, plus 1.9 from the H2. Add that all up, and that ends up being, I think that's like 10.8 or something. Yeah, 10.8. And so I'm just going to divide my 2.1 by 10.8 to get 0.19. That's my mole fraction, right? Or in other words, another way you can say this is that it's 19%, right? 19% of that mixture is the nitrogen. So if I want to figure out my partial pressure of nitrogen, I'm just going to say that, well, apparently the mole fraction is 0.19. The total pressure was given to me at 15.7 atmospheres. And I just multiply those together to get that the partial pressure of nitrogen is going to be 3.0 atmospheres. So I figured out the partial pressure of just the nitrogen. Now I will repeat that for the other one. So if I want to know the partial pressure of the helium, I need to find the mole fraction of helium and multiply that by the total pressure. So my mole fraction for helium is going to be how many moles of helium there are apparently 6.8 moles of helium, and divide that by the 10.8, which is the total, right? I'm just not showing all of the adding, but it's 10.8 is the total. So that I get, let's see here, 0.63, or in other words, 63% of this mixture is helium. So then I go back over here, my partial pressure equation. So 0.63 is what I just solved for my mole fraction. The total pressure is still 15.7 atmospheres, which means my partial pressure of helium is going to be 9.9 atmospheres. So I've solved that one. I've solved the nitrogen one. And then I'm just going to show all of the work, but really if I was being lazy, if I wanted to figure out the partial pressure of hydrogen, it must be the remainder of the total pressure, right? I could add up 3 plus 9.9 and get 12.9, subtract that from 15.7 to get the remainder, but I'll show all of the work, right? So here's my chi, my mole fraction of H2, total pressure. What is my mole fraction of H2? Well, let's solve it. It's 1.9 moles of H2, right? Because that's what it says up here. Divided by that 10.8, which is the total moles. And that's going to give me 0.18, or in other words, 18% of my mixture. And I just pop that in here, right? That's 0.18 times 15.7. And that's going to equal 2.8 atmospheres. So that would be the answer to this question. What is the partial pressure of each gas? Nitrogen is apparently 3 atmospheres of that 15. Helium is apparently 9.9 atmospheres of that 15.7. And hydrogen contributes 2.8 atmospheres. And sure enough, you should always double check. If I add them all back up, if I add the 3 plus 9.9 plus 2.8, it equals 15.7. So that's how all of those pressures combine to give me that total of 15.7. Now I want you to pause and take a crack at this one. Similar type of question with a little less work, but pause, see if you can figure out the mole fraction, right? You're gonna have to convert your percentage into a mole fraction, which is very straightforward, and then solve this. Okay, so let's take a look at this problem here. A scuba diver descends to 40 meters. At this depth, the pressure of air she breathes is 4.01 atmospheres. given that she is breathing, spelling error, that she is breathing nitrox, which is 32% oxygen and 68% nitrogen, what is the partial pressure of oxygen she is breathing? So this is asking me for the partial pressure of oxygen. So partial pressure of oxygen, which means I'm using my partial pressure equation here. I need to find the mole fraction of the oxygen, and I'm going to multiply that by the total pressure. Now, I don't have the moles of everything, but I do know that the mixture is 32% oxygen, which is just telling me the mole fraction. It's telling me that the mole fraction is 0.32, right? Remember that those decimals can be converted into fractions from all of your old math stuff, right? You know, dust off your old math ideas. You probably learned that at some point. So I already know that my chi here, my mole fraction of O2 is 0.32. So it's going to be pretty straightforward. I just need to pop that in here. And my total pressure, they said, was 4.01. And then I just multiply those together. So apparently my partial pressure of oxygen is 1.3 atmospheres. That's it. So we can use this Dalton's law of partial pressures to find a total pressure by adding up all the partial pressures. But we can also figure out what's the contribution from one gas's partial pressure to the total pressure like we just did here. So do a lot of practice, study up, ask me questions. Good luck.